Okay, so this is my second topic for the day. For those of you joined in, I am Narayana Prasad Athreya from Cavium. I am the Associate Director of Software Engineering, and my team works on OCTEON and OCTEON TX processors in our line. Specifically, we focus on accelerators embedded in our silicon. And this is the second topic today, and it focuses on the work we have done to add support for PCI-e EndPoint in OpenDataPlane. So let me go ahead and give you a background of what we're talking about here. So PCI-e EndPoint is the target mode of operation for PCI Express specification. So typical devices that come under this umbrella are NIC devices, you have graphic cards, you have security co-processors. They all tend to be plugged in on the PCI bus with a controller acting as a master. So the PCI bus, which is the channel between the master and these devices, is used for both control plane operations, where you have to configure things, status retrieval, and also for actual data exchanges. We'll talk about more in detail on that aspect. Quick background again on ODP for those who are unaware. So ODP is the networking data plane API specification that allows applications to be built in a vendor neutral manner, portable manner, while still being able to leverage all the hardware specific, vendor specific hardware. So this is the conventional ODP usage. So you have a host, or you have your main processor on which your ODP application runs. The ODP application is the master for NIC devices as well as any co-processors that exist. So it controls those devices basically. And the last bullet is key, and I'll clarify that again. So see, the ODP application, ODP API spec today does not enforce or guide applications on how the control plane aspect of the application is built. It's focused on data plane, which is good. But there is an aspect of control plane, and I'll highlight that element again as I go through my slides. So just to repeat, the ODP API does not guide on the control plane implementation. This is what we have as a use case. What we have is an OCTEON TX device that is plugged into a master controller. It acts as the endpoint. The host system in this case is the root complex, the PCI root complex. And the ODP application is now running on the target and not on the host. So that's the key differentiator here. So in this case, you have the application that's sitting on the target, but then is being controlled by a master that's running on a different processor altogether. The ODP application can still be the master for the NIC ports because it's still running on the actual device that hosts the NICs. So the key differentiating factor between the previous use case and this one is that the PCI pipe is used both for control and data plane. So that means as an ODP application sitting on the endpoint, the ODP application must know how to talk to the host because it's the same channel that's used for both control and data. So you cannot have a situation where I have written a driver or a data plane application that works on the PCI and completely ignores the control messages that comes on the same bus. So that's one key aspect that I'm trying to highlight here. I'll again emphasize that in subsequent slides. So just to reiterate, there are two types of data exchanges that are possible on the PCI bus. One is network packets. So these are your data plane packets. They can have L2 headers, L3 headers, typical IP protocol packets that you exchange with the host. The second is a custom message, or transport, if you will. The difference between the first and the second is that in the first case, the hardware can be aware that it's a network packet. But in the second case, the hardware cannot interpret the data. is just raw opaque data. So you cannot parse it, you cannot treat it like an IP packet, you cannot do any of those stuff. Now, typically this is used in a request response mode, tends to be driven in the control plane atmosphere, but then we also have use cases where customers have used this for data plane. So for now, I've just segregated those as two different forms of data. One is formatted network data, the second is unformatted opaque data. So based on that, I will illustrate to you two code sequences that show how we managed to use the ODP API to handle those two situations. So the first one is the simpler one because ODP is a networking data plane API, so it was easy to project the host as a NIC device. So that's what we've tried to do. Let me highlight the code here. So what we did was we registered our own packet IO here. So SDP is the OCTEON TX internal PCI block simulating a packet device. So we register that as a packet IO. That's where all our driver sits. And then the subsequent API should be very familiar for anyone who's worked on the ODP API. You go ahead, query the capabilities of your packet device basically, set up your queues, how many descriptors, what buffers, and then you kickstart your packet IO. This is your standard boot sequence. Once that's done, now we are onto the data plane. Now the data plane looks very, very simple. All you have to do is pick up packets. For example, in this example, what I'm doing is picking up a packet from the host, sending it to the wire, picking up a packet from the wire, sending it to the host. So you could use any of your methods. For example, in this case, I've showcased the event method. You retrieve the packet from the event, process it, send it out. You could use the packet in receive API. So all the existing API become immediately available to simply exchange packets with the host. So we were able to use this existing API as is pretty much without any changes to hook up our PCI data plane. And now we have a situation where the ODP application running on the endpoint is acting like a miniature L2 switch, if you will. So now we talk about the second approach, or the second scheme, if you will. So in this case, now the PCI endpoint, or the host, is projected as a coprocessor. So we differentiate between the two in terms of how you talk to them. So for a coprocessor, it's opaque data. You give the coprocessor some data, you expect a response back, and it's purely the application that knows how to handle it. The driver is merely a transport to send and receive the data. So when we looked at how we would do it with ODP, we realized the same packet IO interface can be used to do the same thing. We deliberately register it as a different device because it goes through the channels where the packets don't get processed or don't get treated like a network packet or an IP packet. So you once again register a packet IO. This time it's our DMA, TMA engines, and the sequence is again similar. You query the number of queues that the packet IO can support, you configure the queues and the descriptors, and you kickstart your packet IO. Now once we have gone through the packet IO route, life is easy because you can use the existing API to send and receive messages or send and receive data. So we just used, for example, the send to initiate a request, and then the response came back as an event from the host side. So the message goes all the way up to the host. There's software setting on the host which would send the response back, and it comes back as a buffer. So this is a very simple sequence. There's no reason why the same sequence cannot be the other way around. Even though I have said the request is initiated by the ODP application in this case, you can easily envision a situation where the host initiates a request and you're the one responding to it. So the ODP application is the one responding. So imagine a query for statistics or something of that sort. So both these two sequences can be altered. So this is something dynamic. Just to recapture what I just talked about in a broader block diagram. So we have a host driver sitting on a host CPU, maybe an Intel or an ARM. And we have these internal hardware blocks. This represents the block that tends to parse it as a packet, and this represents the block that treats the messages as opaque data. And then we have internal blocks in our OCTEON processor for packet input, a packet scheduler, as well as a packet output. So if you trace the blue line, it represents a packet coming from the wire. So the packet comes in from the wire into our packet input hardware. One of the cores picks it up and decides, if I refer back to the previous sequence, it decides, hey, this is a packet from the wire, I need to pass it to a host. So it sends it out via the PKO. Now the PKO is configured in one of the queues to internally post it to the SDP block. So that's why the dotted line. So that's an internal. So the CPU doesn't participate there. So that's an internal arc. And the SDP block sends it over the PCI. So you have a packet that came from the wire, goes through the ODP application running here, and then it's reached the host driver. Similarly, now the host driver wants to send a packet out. It sends it over to the SDP. There is a dotted line hooking the SDP to the packet input block. Once it's available here, the ODP application running on the core picks it up like it picked up the packet from the wire, and then sends it out over the PKO and out to the wire. So this sequence is what we use in our current NIC, intelligent NIC firmware. So we can run our bare metal NIC firmware on our card, NIC card, which plugs into our host today. And our thought process is to have ODP sit here. The green line is used for control today. For example, the host could initiate a request. It would go to the DPI block. That would, internally again, the DPI block is wired in our hardware to the PKI. That causes an event to be triggered. One of the CPU cores picks up the event, realizes, hey, it's a request from the host, processes the request, and then responds back via the DPI block. So that's the sequence for the green line. So all these packet sequences can happen in parallel as part of our application today, and our vision is that we would replicate all of this with ODP identically. So that's the plan. A quick review of status. A lot of what I said here is actually heavily work in progress. Some of it is actually conjecture. We think that's how it would work out. We haven't actually implemented some pieces of it. We are aggressively working on it and hope to validate what I've just proposed here. In case we realize something is not in place, we may come up with an RFC where we need some adjustments to the ODP API or what we realize. Once again, our roadmap is to run performance benchmarks eventually, compare it with what we have today as our bare metal firmware, and see how it pans out for ODP firmware. So that's, in short, what I have. Q&A. Yes, sir.
That looks pretty exciting. So I think I've understood what you've done, and I have a question on how far can we go and extend things. If we assume that we're in a virtualization environment and we have VMs running virtual domains, would it be possible to give ODP instance inside the OCTEON TX, let's say the memory blocks on that VM, and then create the virtual descriptors inside those areas so that OCTEON TX will deliver directly to virtual format to the VM? Is it something that...
So in our example is the VM running on, whenever we talk about our situation, we need to know where is the VM running. Is it running on the host or is it running on the endpoint?
So the ODP would run on both in the VM, or maybe it's not even ODP the VM. Let's say it's DPDK.
Okay, so that's on the host. So that's on the host.
So you have
Right.
a DPDK VM on the host, and you have an ODP application on the
this arrangement allows us to do things like inline IPsec readily on our firmware directly. We don't even have to, so it's almost like a bump in the wire if you want to do it. Absolutely, that's not a problem. So the host side stands opaque. So in fact, in the whole discussion, we do not have to touch our host side code at all. The idea is to just replace our current firmware with the ODP-based implementation, and we want to support the same messaging formats that we support today, and the host driver or the host code remains unchanged. So, but I see what you're saying. You have a different idea where I can format it something differently, and absolutely. Both the green, if I can quickly go back once. So all three lines can be used for both control plane and data plane. So you're limited only by the PCI bus bandwidth. The format of the message dictates how much hardware processing is done. For the orange and the blue lines, you are deliberately going through a block that will treat it as a network packet. For the green, it's an opaque packet. So you skip the hardware packet processing. So you're right. You can add custom headers to it. You can do other types of processing before you send it over to the host.
I have another question. You say Cavium host driver. Is it possible to link just on the back end on the OCTEON TX? This is the ODP instance. Is it possible to think of a standardized PCI device with a standardized host driver that will accommodate any ODP-enabled small bit? Or do you think it is always?
Yeah, I mean that probably falls a layer above what it is. That's application formatted data. So the application running here and the application running here, code running here and here know what data to expect. The hardware, for the hardware and ODP, it's all opaque. As long as you're not interpreting any of the data, you're free to implement your own custom protocol over this channel. Absolutely.
Using the host driver, right? The driver bases on the PCI Express link, and the host driver would be inaccurate.
Yeah,
Implementation only, and the smart TV.
absolutely.
Those wire transfers. So let's say if you want to have an ODP line, then this is what you.
Yes.
Just on the Cavium host driver, it's
It could, you can make it a generic. But you would still need, so today it's a Cavium driver because you're talking to the Cavium bar registers or the PCI configuration registers or whatever. So you would need to build an abstraction for the device itself. That probably presents a challenge on the host side, but yeah, if you can come up with a spec or something, doable, definitely doable. Virtual device probably, but doable.
So this means that those who are working on the VASET driver framework inside ODP, we may also want to do the PCI root complex driver.
Yes. So you are right. We have been looking at the DDF proposals. We have been going over that in the background, even though I didn't touch on it. So we have been reviewing that and see where the efforts that we have started fit in that framework. And I agree, we have some crazy ideas there. We don't fully understand the DDF ourselves, but since you're here, we can have more discussions on that. Any more questions?
Is this another thing that you're also planning on RFC?
So right now, when we started off, we thought there may be changes to the ODP API. What we have done so far has not required us to change the ODP API. We were able to use what is there. Granted, there are some shortcuts we have assumed. For example, in our application, we assumed that the event that comes out is equivalent to a word key entry, which is a hardware notion. So some of it is not done in a opaque fashion. We may have to improve on that. So we're not ready for an RFC yet. This will probably take at least another 1 or 2 months worth of work before we can.
Well, I guess one of the questions is, for you talk about transferring packets. If it truly is a direct transfer, the application is doing anything other than pushing the
can always boil it down, say, can I set up something in hardware that quickly transmits it? So it's up to you to how you want to do it. But so one of the reasons we have this application is not just to do the basic packet transfer. We tend to do a lot more with the packet. That's why the term intelligent NICs. In other words, it gives our customers the ability to do more with the CPU code, to program it, do custom things that the hardware otherwise cannot do.
You get early sniff packets before they get to the
Exactly. So that's where this really comes in. If you were just going to do it in hardware, you could just use a regular NIC. You don't need this. Yeah, if anyone else has any questions, I'm here for a few more days. Catch me whenever you want on both these topics. And yeah, we can have a chat. All right then. Thank you. Thanks everyone.